Hello and welcome to our electrochemistry video project. We'll be starting with the understanding of oxidation and reduction reactions. Firstly, we'll talk about oxidation reactions. So what are oxidation reactions? Well, it is the process where a molecule, atom, or ion is losing their electrons. And here I have an example of rusting in iron. When iron rusts, iron atoms are losing electrons to oxygen to form the iron oxide. And for reduction, we are doing the opposite of an oxidation, which means we're going to gain electrons. And using the same example of rusting, in this process, oxygen will gain the electrons from iron to form the same iron oxide. Next, we have the combination of both reactions, known as redox reactions. As I just said, they are when both processes are occurring simultaneously. And an example of this would be when hydrogen gas reacts with oxygen to form water, hydrogen is oxidized and the oxygen is reduced. So here...
Hi, I'm Qiqi, and after Samantha's introduction, I'm going to introduce you to oxidation numbers and some rules. Oxidation numbers are a system used by chemists to keep track of electrons during redox reactions. It represents the apparent charge an atom would have if the electrons in covalent bonds were assigned to the more electronegative atom. In this system, oxidation numbers help to identify which atoms are losing electrons, oxidation, and which are gaining electrons, reduction. The key idea is that electrons in a bond are assumed to belong entirely to the atom with a stronger attraction for electrons, which are more electronegative. For example, in water, H2O, oxygen is more electronegative than hydrogen, so we assign all the shared electron to oxygen. As a result, oxygen has an oxidation number of -2, and each hydrogen has an oxidation number of +1. The oxidation number system is useful for electron bookkeeping, but it doesn't represent the actual charge of an atom. It's more of a conceptual tool. Alright, now that we're done with the key definition, let me introduce you to 5 rules of oxidation numbering. The first being, an atom in an element is 0. The oxidation number for any atom in its natural element state is always going to be 0. This rule applies to elements that exist alone, such as sodium metal, oxygen gas, or even ozone, and those that are diatomic or in pure form. An example of that is sodium in its solid form. Moving on to the second rule, a monatomic ion is the same as its charge. For ions that consist of a single atom, known as monatomic ions, the oxidation number is equal to the charge of the ion. This means that the oxidation number is positive for cations and negative for anions. Some examples of it include sodium ion, Na+, oxidation number will be +1, chloride ion, Cl-, oxidation number will be -1. The third rule only involves one element, fluorine. Fluorine is -1 in its compounds. Fluorine is the most electronegative element, so in all of its compounds, it has an oxidation number of -1. This rule holds true in compounds like hydrofluoric acid, HF, and phosphorus trifluoride, PF3. Moving on to the fourth rule, oxygen is usually -2 in its compounds, except in peroxides. Oxygen typically has an oxidation number of -2 in its compounds, but there are exceptions. In peroxide, which contains the O2 with 2 negative charge ion, such as H2O2 or hydrogen peroxide, oxygen has an oxidation number of -1. Some examples of oxygen's oxidation number: in water, H2O, the oxidation number of oxygen is -2. In hydrogen peroxide, on the other hand, the oxidation number of oxygen would be -1. Now let's move on to the final rule. Hydrogen is +1 in its covalent compounds except in metal hydrides. Hydrogen has an oxidation number of +1 in most of its compounds, especially in covalent bonds with nonmetals. However, when hydrogen forms metal hydrides, or compounds with metals, its oxidation number becomes -1. Here are some examples. In water, H2O, the oxidation number of hydrogen is +1. However, in calcium hydride, CaH2, the oxidation number of hydrogen becomes -1. Alright, that was a lot of theory. Now let's move on to 2 practice problems. Let's start with this question. This is a redox reaction, which means it involves the transfer of electrons between 2 species. In order to understand this reaction in more detail, we can break it down into oxidation and reduction half reactions. Oxidation, again, as a review, refers to the process where an atom loses electrons, while reduction refers to the process where an atom gains electrons. Now let's break it down. Oxidation half reaction, where Mg is oxidized. Magnesium Mg in its elemental form loses 2 electrons to form Mg2+. We can write this half equation as what you see above. Here, Mg loses 2 electrons, meaning it undergoes oxidation. This increases its oxidation number from 0 to +2. Now let's move on to the reduction half reaction of H+. The hydrogen ion H+ in the aqueous solution gains the electrons that magnesium lost. 2 hydrogen ions combine with 2 electrons to form hydrogen gas H2, and we write this half reaction as what you see on the slide. Here, H+ gains 2 electrons, which reduces its charge from +1 to 0, forming H2 gas. Alright, let's try to do the same with this question as well. This is another redox reaction. To identify which species is oxidized and which is reduced, we need to look at the changes in oxidation numbers. First, oxidation, loss of electrons. In methane, CH4, the carbon C atom starts with an oxidation number of -4, since each hydrogen has an oxidation number of +1, and there are 4 hydrogens. After this reaction, carbon ends up in carbon dioxide, CO2, where its oxidation number is +4. Since carbon goes from -4 to +4, it loses electrons. This means carbon is oxidized. Reduction, gain of electrons. Oxygen O in O2 starts with an oxidation number of 0 because it's in its elemental form. In water, H2O, oxygen has an oxidation number of -2. Since oxygen goes from 0 to -2, it gains electrons. This means that oxygen is reduced.
Moving on, I will be talking about oxidizing agents. Oxidizing agents is a substance that uses oxidation in other substances by gaining electrons, and in doing so, the oxidizing agent itself will undergo reduction, meaning that its oxidation number will decrease. So here I've input an example, and in this example, the reaction, oxygen will act as the oxidizing agent, and each oxygen atom will gain 2 electrons, and this causes the hydrogen to lose its electrons. Following that, reducing agents. Reducing agents are substances that cause reduction in another substance by losing electrons, and it donates electrons. The reducing agent itself will undergo oxidation, meaning that its oxidation number will increase.
Hi, I'm Maya, and I'll be doing question number 9. So there are 2 parts to this question A and B. The first part is what is the oxidation number of carbon in CO2 and glucose. So let's do that part first. So the 2 we have to focus on is oxygen and hydrogen because we need those 2. So oxygen, reaction I got from earlier, CO2 plus water equals glucose and oxygen, and balance. So let's start with CO2 first. So we know from the table earlier that oxygen's oxidation number is -2, -2. So what we can do is visualize this easier. Because we see that CO2 itself does not have a charge, we know that this will equal to 0 and it will be a neutral molecule. So we can just easily visualize this. So we have -2 and -2 here because we have 2 oxygens and -2 is its oxidation number. So we know when all of this is added up, it will become 0. So now we can write the equation for this. So X will be carbon because that's what we're finding out. And over here we have 2 times -2, -2 being the oxidation number of oxygen and 2 being O2 because it's 2 oxygens. So we can just solve this. So 2 multiplied by -2 is -4, and once you arrange this, it becomes X equals 4. So this means that in 6 CO2, carbon has an oxidation number of 4. So now we can do the same thing for our glucose. So in glucose over here, X again once being carbon, 6 because we have 6 carbons. Over here we have 12 multiplied by 1 because we have 12 hydrogens, and each hydrogen has an oxidation number of +1. And we're plus that with 6 multiplied by -2 because we have 6 oxygens, and each oxygen has an oxidation number of -2.
we can rearrange it. So after we divide both sides by 6, we will get x equals 0. So this means that in glucose, carbon has an oxidation number of 0. Here we have the second part for question number 9, first one, which says the oxidation number of an atom in an element is 0. And an example of this is O2 gas. So now this is our photosynthesis equation. And from earlier, you can see our oxidizing numbers over here, like +1, -2. And as you can see here, the C in glucose and the oxygen over here both have a 0, just because we just saw that in the table earlier. So now we can get into the reduction oxidation stuff. So over here, our first thing is that CO2 is an oxidizing agent. But why? As you can see here, carbon dioxide is reduced to glucose right here. So over here, for oxidizing agent, this is because, as you can see here, carbon has a +4, while this carbon has a 0. As we know, electrons have a charge of -1. So what happens here is that we are accepting or gaining 4 electrons. So because of that, we are having a +4 -4, so that becomes 0. And because we are gaining electrons, that makes it an oxidizing agent. As we said earlier, oxidation means gaining. But the reason why this is carbon dioxide is reduced to glucose is because we are going from +4 to a 0, thus reducing. On the other hand, over here, we have water as a reducing agent, and it is being oxidized to oxygen. So as we said before, reduction means we are losing. So over here, we have -2. So this means oxygen has 2 electrons. And we are getting rid of those 2 electrons, aka we are losing those 2 electrons over to oxygen. So that means that it is a reducing agent because it is losing 2 electrons. But once again, water is being oxidized to oxygen because oxygen is gaining something. Okay, and as you can see here, we have leftover stuff. So this oxygen in this carbon dioxide is just going into this glucose, while this hydrogen is going into the glucose as well. So everything is accounted for.
Hi, my name is Zoey, and I'm going to talk about balancing redox reaction equations. Here's a sample problem from the textbook, page 608. You can pause the video to read it, but let's dive into solving this question. First, we need to write the unbalanced chemical equation, and then determine the oxidation numbers for each element in the equation. Then, to find the oxidation number for nitrogen on both the reactants and product side, we set the oxidation number as x and solve for it by setting the net charge of the compound as 0. For the reactant side, the oxidation number of nitrogen is +5 and +4 for the product side. We then write that copper lost 2 electrons because it went from 0 to +2, which means copper lost 2 negative charged electrons and become a positive ion. Same for nitrogen, where it gained 1 electron as it went from +5 to +4. Then we adjust the values of the coefficient to balance the electrons transferred. During a redox reaction, electrons are transferred from one element to another. Therefore, the total number of electrons transferred must be equal. To balance the electrons, determine the simplest whole number that will equalize the electrons gained or lost in the reaction. Then use those numbers as coefficients. Since we multiplied the number of electrons gained by 2, the coefficient for HNO3 and NO2 must be 2. The coefficient of copper remains unchanged. We can check if the element in the left and right side are equal. Since they are not equal, we multiply HNO3 and H2O by 2 to make them equal. Now we can try to solve another similar question from question 3a on page 617 in the textbook. First, we write out the unbalanced chemical equation and find the oxidation numbers. We can identify that chlorine for the reactant side and iodine from the product side are elements which the oxidation numbers change. Therefore, we need to find those oxidation numbers by setting those unknown oxidation number as x and solve for it. Once we're done, we determine how many electrons the elements gain or lost. The special thing about this question is that there is 2 molecules for iodine, so we need to multiply the 5 electrons lost for 1 molecule of iodine by 2, which result in 10 electrons lost for iodine. Then we use the number that will equalize the electrons gained or lost in the reaction as the coefficient. Finally, we can check if the elements in the left side is equal to the right. As we can see, it is not equal because there is 15 oxygen on the left side, but 18 oxygen in the right side. So we can add 3 water molecules on the left side to balance the oxygen, and then add 6 hydrogen atoms on the right side to balance those hydrogen in the water molecules. Therefore, this will be our final balanced equation.
So this is question 4a. Remember that a molar atomic oxidation number is the same as its charge. The ion is the same as charge. So now this is the equation we have earlier. As you can see, it has charges and everything. So our first step is to put the oxidation numbers that we know from the table itself. As you can see, oxygens will all be -2, hydrogens will all be +1. As you can see here, Cl, because it has a charge of -1, its oxidation number will also be -1. But now as you can see, we have unknown oxidation numbers like for these chlorines and these leads, so we need to find those out. So it's as simple as we've done before. And we can rearrange it. So this will get us x equals 2, which means that is 2. We can do this for chlorine. Once again, because this has a charge of -1, so we put negative on the side, x for chlorine, and -2 because we know oxygen's oxidation number, and we will get x equals 1, so this means chlorine's oxidation number is 1. We can do this for this lead as well. Once again, this doesn't have a negative charge, so it's neutral, so we put 0, x for lead, -2 for O2, multiplied by 2, and we get x equals 4, so this lead is 4. So now we have all the oxidation numbers, we write them down, +2, -1, everything, we are oxidizing. So this lead to this lead, we have a +2 on this side, while over here we have a +4. So we are increasing the number, so that will be oxidation. While this chlorine to this chlorine, we start off with a +1 and we end with a -1. So we're reducing that number, so that makes it reduction. So now we're going to separate the oxidation and reduction into 2 separate equations. So over here, we have our oxidation equation, and over here we have our reduction equation. So these are going to be our half reactions to make everything easier. So next thing we want to do is write down our reduction half reaction. So over here, we can add a hydrogen, so we can have equal amounts of oxygens. But as you can see, now we have 1 oxygen on each side, so those are balance. But now we have 2 hydrogens on the product side. So that's not what we want, so we have to move on to the next step, and that is balancing the hydrogens. Our next step is, because this is in a basic condition, and we have just a lone H plus here, we can't have that. So now we have to add minus OH minus to whatever H pluses we have. And we also need to balance that on both sides. So as you can see here, we added 2 OH minus to this side, making it 2 waters. And over here, we also have 2 OH minus because we added 2 OH minus on the reactant side, so we have to add it to the product side as well, just to balance it out. Okay, now that's done. Now we have both our reduction and oxidation half reactions back. So now we need to balance the charge. As you can see here on the reactant side, we have a 2 minus here, so we're going to add a 2 minus on the other side. And as you can see over here, we also have 3 minus on this product side, so we're going to have 2 minus on this product on the reactant side, since we already have 1 minus here. Our next step is we just need to add these two together. So we get this really long equation. So we need to simplify this. So we cross out whatever we have multiples of on both sides. So as you can see here, we can just cross out both waters, but this has 1 water left, and we can cancel out the 2 electrons on both sides. So now we get this. This is our equation. As you can see, we've simplified it. So now we can check if our equation is correct by doing more tables. So over here, we can check the elements on the left, the reactant side, and the right, the product side. And as you can see, we have the same amount of elements on each side. Next, we can also check the charges, which are highlighted in yellow. And there's -3 on the left side and -3 on the right side, which means it is also balanced. So finally, this is our balanced equation.
Hello, my name is Cindy, and now I'll be describing how this table can help us identify whether a reaction will occur spontaneously. So, based on this table, we can interpret it by reading it from the left to right, meaning we'll be seeing the reduction reactions, or we can read it from the right to left, meaning we'll be seeing the oxidizing reactions. So the strongest oxidizing agent, labeled as SOA, is at the top left of the table, and the strongest reducing agent, labeled as SRA, is at the bottom right of the table. So we can see that reactions can occur spontaneously when the oxidizing agent is combined with the reducing agent below it on the reaction table. This is because the oxidizing agent, which is higher up on the table, has a higher tendency to accept the electrons, while the reducing agent that is lower on the table has a higher tendency to give out electrons. This means that the electrons will flow naturally from the reducing agent to the oxidizing agent. For example, the oxidization silver will react spontaneously with the reducing agent magnesium. This can be drawn by using a diagonal line from the left to right with the condition that it involved an oxidizing agent above the reduction agent on the table. For instance, if we were to combine the oxidizing agent Mg2+ with the reducing agent silver by drawing a diagonal line, there would be no reaction, as the oxidizing agent is below the reducing agent on the table. This is because when the oxidizing agent is lower on the table, it will be less likely to accept electrons. Therefore, the arrow on the left of the redox table depicting the decreasing strength of the oxidizing agents. And when the reducing agent is higher on the table, it will be less likely to give away electrons. Therefore, the arrow on the right of the redox table depicting the decreasing strength of the reducing agents. Based on this, the reaction won't occur spontaneously, as the oxidizing agent is less likely to accept electrons, and the reducing agent is less likely to give away electrons. So now, I'll be ending off this presentation by giving you a quick paragraph conclusion of what we've learned. At this point, you can pause this video to quickly read the paragraph conclusion, as I'll be explaining this by breaking down and summarizing each subtopic. So now we can be using the mnemonic oil rig to help us understand oxidation and reduction. So oil stands for oxidation is loss of electrons, and rig stands for reduction is gain of electrons. So what exactly are redox reactions? Well, they are when electrons are transferred between two reactions, and one will gain and the other will lose electrons. The loss of electrons, which increases the oxidation state, is known as oxidation, which is a reducing agent, while the gain of electrons, which is the decrease of oxidation state, is known as reduction, which is an oxidizing agent. Redox reactions can be broken down into half reactions for both oxidation and reduction specifically. Now, if we compare the number of electrons in the two half-reaction equations, we can see that the number of electrons is not the same. In a redox reaction, the number of electrons lost by oxidation must always equal to the number of electrons gained by reduction. What are oxidation numbers? Well, they help to keep track of the number of electrons in the oxidation-reduction reactions. So, let's think about the oxidation numbers for atoms in a covalently bonded molecule. First, we should understand that the atoms share electrons in covalent bonds. You can determine the oxidation numbers of atoms in covalent compounds by assigning the shared electrons to particular atoms. In covalent bonds between two identical atoms, the electrons are shared equally. However, in cases where a covalent bond exists between two different atoms, the atoms share the electrons unequally. When assigning oxidation numbers, the shared electrons go to the atom that has a stronger attraction for electrons, which is the more electronegative atom. For example, in a molecule of water, oxygen is more electronegative than hydrogen. When assigning oxidation numbers to oxygen and hydrogen in water, you assume that the oxygen atom actually possesses all of the electrons, even if the electron is shared with hydrogen. Remember that hydrogen atom has one electron. Therefore, in water, you assume that the oxygen atom has taken the electrons from the two hydrogen atoms. This gives the oxygen atom an excess of 2 electrons. Then the oxidation number of oxygen is -2, and each hydrogen atom has no electrons, and is given the oxidation number of +1. Now moving on to balancing redox reactions. We can do this in two ways. The first way is using oxidation numbers. So the steps are written as follows. Write the unbalanced equation, determine the oxidation numbers, and identify the elements for which the oxidation number changes. Then balance the number of electrons transferred by adding coefficients. And you should just check your answer by ensuring that the sum of both sides are equal, and then write the balanced equation. Redox reactions is by using half reactions. It's a little bit longer, but I feel like this would be a lot easier to understand. So first, we write the unbalanced equation and assign oxidation numbers. Then you write the unbalanced equations for the oxidation and reduction half reactions. Then you balance the half reaction equations and use the electrons to balance the charge in each half reaction equation. Then you ensure that the number of electrons in both half reactions are the same. You add the half reaction equations together, check your answer, and then write the balanced equation. So here we can see how do we predict redox reactions. This can be seen using the redox tables that I mentioned in the previous question, which I've already discussed thoroughly. However, the stronger oxidizing agent needs to react with the stronger reducing agent in order for a reaction to occur spontaneously, as both elements will be more willing to give away and to accept electrons. And thank you for listening to our presentation, and I hope that you were able to understand redox reactions effectively. Bye bye!